Hi everyone. So we're about midway through week 5 and the second half of module 3. And so before I get into the lecture video, I'm going to go over a few upcoming due dates and to discuss the midterm a little bit since it opens up Thursday at 6 p.m. And that's Thursday, September 24th, and it'll be open through Tuesday. So you guys should be working on discussion 5, maps and social equality, which is due this coming Tuesday, September 29th by 11:59 p.m. There's no lab this week because I want to give you guys enough time to review for the midterm and the open lab on Thursday evening. I'll be doing just like a really brief overview of some of the content that we've gone over, focusing on people's muddiest points from each lesson. And then if you have any questions, I will try to address them either in the open lab or in a follow-up, depending on the content of that question. So again, the midterm opens Thursday, September 24th, 6 p.m. and is open through Tuesday, September 29th, 11:59 p.m. I suggest that you spread out your 2 attempts, take it earlier on in that time frame after you feel, that you've reviewed the content enough, and take note of the questions and what's on there. And then take a little break, like if you can, give yourself like a day or 2 just to go over everything again and have a fresh mind when you go into that second attempt. There will be around the midterm is worth 100 points, and there's 2 hours to take it. So I just don't want you guys to be stressing on Tuesday, trying to take your 2 attempts within that one day. So just a little tip. Okay, so let's go ahead and get into the lecture. We'll be talking about spatial reference systems. A spatial reference system defines geographic location and may include the map datum, the coordinate reference system, and the map projection. Be aware that many commonly use the term coordinate systems to refer to spatial reference systems. This is not entirely correct. A coordinate reference system is more specific in that it refers to a coordinate-based reference system to define location. Some spatial reference systems, like the land partitioning systems, do not have coordinates and use other means of determining location. We'll be getting more into land partitioning systems in Module 4, but we'll have a brief introduction during this lecture. So coordinate system is the most general term for a system that includes coordinates, and spatial reference system is a coordinate system used to reference spatial information, typically to the surface of the Earth. You'll see these 2 terms and their acronyms used interchangeably in GIS. So we went over this briefly last week, and so we'll go over them a little bit in more detail today. So there are 2 types of coordinate systems. We have geographic coordinate systems, which is based off of a 3D spatial model or off of an ellipsoid, and then a projected coordinate system, which is based off of a plane or Cartesian coordinates. So you have one, the GCS or geographic coordinate system, that's calculating its locations based off of a sphere with gradicules, with parallels and meridians. And then you have a projected coordinate system, which is projecting onto a flat surface. I want to highlight this point here really quick. All projected coordinate systems are based on a geographic coordinate system, and all coordinate systems are based on a datum. So a geographic coordinate system and projected coordinate systems will all have datums included in their calculations, and you'll see that when you review metadata. But what happens a lot and where there can be a lot of confusion is that in a projected coordinate system, when you're looking at the spatial reference system in ArcGIS or whatever GIS program you're using, it'll show a projected coordinate system and a geographic coordinate system, because the projected coordinate systems still need a reference ellipsoid to be able to calculate the coordinates, where the, because it's representing the, closer to what the shape of the Earth is in that reference ellipsoid rather than onto a flat surface. So that PCS needs the GCS, where a geographic coordinate system doesn't need a projected coordinate system because it's already based on a three-dimensional model. And all of this is a lot of information. It can be kind of confusing at first, but it'll start to make more sense once you guys start using ArcMap more and getting more familiar with the program, especially because we'll be working a lot with projections, and we need to make sure that all of our projections are in the same spatial reference system. And we'll get into that a little bit more next week with one of the labs that we'll be completing. A geographic coordinate system is a coordinate-based spatial reference system using latitude and longitude. An important fact to remember is that a geographic coordinate system is ellipsoid-based, which makes it useful for defining a location on the surface of the Earth. However, a geographic coordinate system makes measuring distance in areas complicated. Geographic coordinates are traditionally written using degrees, minutes, seconds, or DMS notation. And we can see that here. So degrees, minutes, second, and then we have north or south. And then we have, again, degrees, minutes, and seconds for east and west. So you'll see this order a lot. And so we're always going to see latitude first and longitude second. And so what we have here is 40 degrees, 45 minutes, and 27 seconds in the northern hemisphere. And then with the east-west, you're always going to have these triple digits. So 124 degrees, 7 minutes, 30 seconds, and western hemisphere. I know this may seem redundant, but I'm just going to go over it really quickly again. Using this notation, degrees is the number of whole degree, minutes is the number of minutes, and seconds is the number of seconds. And at the end, you'll have the letter N for locations north of the equator, and S for south for latitude, and east for locations east of the prime meridian, and west for west of the prime meridian for longitude. Sometimes it's necessary to convert the traditional notation into an alternative decimal format called decimal degrees. Using decimal degrees makes it easier for GIS software to manage coordinates because it can treat latitude and longitude coordinates as decimal-based numbers. And so when we upload coordinates into GIS and into a GIS like ArcMap, you'll be using decimal degrees. And there's usually pretty easy conversions either on the internet or even within ArcMap itself, and we'll be going over those in the future as well. But one thing that's really nice is, if you're using an app like Google Maps or Google Earth, something like that, most of the time when you put a pin down, it'll give you those decimal degree coordinates as an option rather than just the traditional notation of degrees, minutes, and seconds. So sometimes you have to determine geographic coordinates on a map in a place that does not line up with any specific latitude or longitudinal marking. You would do this by measuring the proportional distances between latitude and longitude indicators on a map. For example, the USGS Arcata North 7.5-minute series quadrangle indicates latitude and longitude with a series of black tick marks just inside the neat line. And I know that this is a pretty small graphic, but there's little marks here along this quadrangle. And the neat line, again, is that the border of your data on a map. The USGS sets each of the tick marks 2.5 minutes apart. You can use these marks to calculate coordinates for any point on the map. Suppose you would like to find the geographic coordinates of the Arcata Plaza. The plaza does not land exactly along one of the tick marks on the map. Since the exact distance between each tick mark is a known quantity, this is not a problem. So to define the geographic coordinates, you would measure on the map the proportional distance across to the next tick mark between north and south for latitude, and between east and west for longitude. You could then use these proportions to calculate how many minutes and seconds to add or subtract from the nearest tick mark depending on the direction. Okay, so spatial reference systems and why we should care. We need a common locational frame or reference in order for our layers to line up correctly in order to derive spatial information about the real world from our GIS. So if you remember from the last lab, not all spatial reference systems use the same calculation. So if your different layers that you're using in your map aren't all in the same spatial reference system, you're not going to get an accurately displayed map of your data. Also, your layers won't line up, and so things will be off and they won't be geographically correct.